Welcome everybody to Integrability Journal Club. And today I'm very happy to welcome Nikita Nekrasov from Simon's Center for Geometry and Physics, who will tell us about Lefschetz thimbles in field theory. Please, Nikita.
Thank you very much. So this talk is based on my recent work and more recent work with Igor Krichever and on his students. So before I proceed to the actual topic of Lefschetz thimbles in field theory, let me just remind you the concept of Lefschetz thimbles in a zero-dimensional field theory, namely in computations of ordinary exponential integrals. So we have some real manifold with some function s depending on parameters, and we would like and measure dx. So we would like to integrate the exponential of this function, and we assume there is a small parameter h bar, which we call h bar, which we may want to expand in this parameter, or we may just want to study the function in the domain when this parameter can be taken to zero. But we're interested in the periods of this exponential measure as a function of the parameters of the thing in exponential. And usually, what you do, you guess or derive some differential equations which these periods obey, and then typically this would be differential equations of high order, so we will have many solutions. So there is a geometric answer to the question of what is the what kind of multiplicity, what kind of what is the dimensionality of the space of solutions of these differential equations, or put differently, if I start varying the parameters. And so if I do analytic continuations in these parameters, so how many branches would this function have? What kind of behavior should I expect? And the way to approach this problem is to view this original exponential integral as the period in algebraic geometric sense. Namely, imagine that this space on which you integrate x admits a complexification. So there is some complex manifold in which x is the original x is like the middle dimensional submanifold, and this measure and the function in exponential admit the analytic continuation to holomorphic to the holomorphic top form, which I denote by omega, and some holomorphic function on this complexification. So this original integral becomes like a period of a holomorphic object over the middle dimensional subvariety, and then you can expand this cycle, this original cycle, which we're integrating over in the homology, in appropriate homology. And the appropriate homology is the relative homology of this complexification modulo the subspace where the real part of the exponential is very large, so where the integrals converge. And so that's typically so it's vector space of some dimensionality, and you can choose some basis in this vector space, which I denote by gamma A. So A for the moment just runs through some set of labels which label the basis in space. And then there is a homological problem. So this original cycle x in the homology can be expanded in this basis with some multiplicities and a, which are integers. And so your original integral decomposes as a sum over the of the same basis with the same coefficients and a of the periods of this form over these cycles which form the basis. So these multiplicities themselves can be computed by some kind of intersection theory. When you intersect over dual cycles, your original real slice. But it turns out that, well, so in principle, so these dual cycles form the basis in the space where you take relative homology with respect to the subspace X minus, where which would be suitable for the integrals with the opposite sign of the Planck constant. And it turns out that there is some kind of, in some sense, an optimal representative for this cycles gamma A. It's actually not unique, but there is a class of these representatives. And the way they are constructed is as follows. You start at the critical point of this function S. So, so this A turns out to label the critical points of the function. And then you run the steepest descent. More precisely, you look at all gradient trajectories of the function, the real part of S divided by H bar, the gradient in some Hermitian metric, and that's the ambiguity. So you can choose this Hermitian metric any way you like. And so you look at all the trajectories which emanate from the critical point. So these are trajectories along which the real part grows. And so, so in some sense, this is a trajectory where the real part grows in the fastest possible way. And so the exponential of minus S over H bar decays as fast as possible. And so, so your integral converges in a sense, again, in an optimal way. So, well, there are several, a priori, there are several critical points. And so that confirms the quasi-classical intuition that the number of solutions of this well, differential equation, which I talked about, should be of roughly of the order of the number of critical points of the function. So locally, so near a non-degenerate critical point where the function is the same, can be approximated by the sum of squares, assuming it's a non-degenerate critical point. So here, the real part will have the roughly the form of the difference of the sums of squares of the real and imaginary parts of the coordinates. And so the Lefschetz thimble, which is the span of the gradient trajectories along which the function grows, will correspond to setting the coordinates which enter with negative squares to 0, and just taking the trajectories which start as linear flows in the variables which enter with positive squares. And then there is a dual Lefschetz thimble where you reverse the sign of H bar, and that will be given by the opposite. So you set X to 0 and flow in the Y direction. So that's the very fast introduction to the topic which occupies a big portion of singularity theory in mathematics. It's a study of the possible critical points and what's the effect in the exponential integrals. Things like, so let me just mention some names. So Picard-Fuchs equations, Gauss-Riemannian connection, well, the usual WKB approximation. And so these are all things, and then more recently the whole singularity theory. and notions which that theory brings, like vanishing cycles, Picard-Lefschetz monodromy, and so on and so forth.
So it is essentially about small h bar limit. Yes. So is this, that equality is asymptotic for small?
No, it's exact state. It's an exact equality. It's just that small h bar gives you an intuition for why you choose this. Why would you choose those cycles? No, there's no. It also gives you a kind of understanding for the lack of convergence of the h bar expansion. So so also by thinking about these integrals and these expansions, you can also understand some notions of resurgence. Borel transform and so on. So this is Stokes phenomena, all these things which people talk about. So usually, if you pick one critical point, which need not to be on the real slice, where you started, and then you can start by approximating each period by the Gaussian integral, and then doing the perturbation theory, and that series will of course will be asymptotic because the real function knows about the presence of several critical points and several cycles. So the interaction between these different critical points that leads to the various features of the asymptotic series, which you get by picking one critical point. But I just want to classify those cycles and get an understanding of what they are. And so here is the motivation, which is more physical, well, which is, I find more amusing. So if we go to the now lift from 0 dimensions to 1 dimension, study and look at the quantum mechanical problems. So suppose I have some quantum mechanical system, which is a quantization of a classical system with Hamiltonian, which has some analyticity property. So for example, let's say the Hamiltonian is the sum of the kinetic term and the potential let's say, is a polynomial. And I want to evaluate the trace of the Euclidean time evolution operator to learn about the spectrum of this Hamiltonian. So I can formally write it as a path integral. So on one hand, it's a trace over the Hilbert space, not the Gilbert space. But on the other hand, it's well, it's given by the Feynman path integral over the periodic trajectories. So essentially, it's an integral over the space of loops, maps of the circle into the phase space. And then, since we want to have the Euclidean time evolution, we do the usual weak rotation, which in the phase space language, it keeps the term, which is the integral of PDX, which is like a canonical term. And then the contribution of the Hamiltonian is now become exponential. So it's instead of oscillating, it becomes exponentially suppressing. And one useful remark is that, of course, this function, this partition function as a function of beta, the Euclidean time or inverse temperature, actually is an analytic function. So this beta, this is one of the parameters which I'm actually allowed to take complex. Of course, this function may have singularities, may have some well, singularities when beta, let's say, approaches the imaginary axis, where the operator of evolution becomes the truly unitary operator, and so its trace might be not well defined. But at least when the real part of beta is positive, this and the Hamiltonian is reasonable, this function should be well defined. So how do I represent it by the path integral? I cannot use the standard sort of physical definition where my time is periodic with the period beta, because beta is complex. So instead, what I do, I rescale time. So I put beta in front of the integral of the Hamiltonian, and then just use the parameterization when the period of my orbits is just 1. So then the integral is from 0 to 1. The trajectories are periodic, but beta is simply the coefficient of the Hamiltonian. And then, of course, that way beta can be made complex. So we'll encounter this similar these tricks in higher dimensions, and they're just important to understand how it's done in the simplest case.
You complexify beta, but the volt sheet it's still a real manifold.
That's very important. Yes. So the complexification, the analytic continuation of all these visible quantities does not imply that the word line becomes a volt sheet. The word line remains a word line.
Mm-hmm.
So in all this, well, if we follow this logic, when of the exponential integral, we need to complexify the space over which we integrate. So our space over which we integrated in the textbook definition of the trace was the space of loops valued in the phase space. I mean, in Feynman textbook, you actually integrate over loops in the configuration space, but if you go to Faddeev-Slavnov, you learn that you can also write the loops in the phase space. That's the definition which turns out to be much more useful. So Feynman actually misses certain thing, and I will explain what. So then the question is, how do you complexify this space of maps of a circle into the manifold? Well, if you think of it as over infinite, so if you think of the space of maps of loops, it's like the infinite product of the manifold itself. So as many times as the number of points in the circle, then to complexify the space is really just to complexify the phase space from that point of view.
And also you need top holomorphic form as analytical continuation for the measure.
Right. So the measure in this phase space integral is just like a pointwise product of the symplectic volume forms. And so when I complexify my phase space, oh sorry, I'm already going to the example. So the so I'm sort of jumping ahead of time, but so I will replace the phase space by its complexification. And by that, I understand the complex symplectic manifold. So the symplectic form will also get complexified. So it's dp dx, where now p and x are complex. Mm-hmm. And so that way, this becomes the holomorphic top degree form. Okay, so but we're not there yet, because so it is just what is going to happen. But let's look at how this happens in the classical quantum example. So the example which I like to start this lectures is the example of the anharmonic oscillator, because it's a textbook example where people motivate the instanton methods, which sort of, and the instantons are sort of these saddle points which are somewhere in the complex, in the space of complex fields. But what is usually said in textbooks, I think it's plain wrong. So that's I'll try to correct that. So okay, so what's the problem? The problem is indeed the textbook example. It's double well potential, which I'll take to be of the Higgs type. And so classically we have two vacua when the particle sits at the bottom of either left or the right wells. And quantum mechanically we can look for the wave functions which are the approximately Gaussian supported at either left or right minimum of the potential, and do the perturbation theory in H bar and get perturbatively doubly degenerate spectrum, because things look exactly the same on the left and on the right. And we know that that cannot happen thanks to Feynman and his, for example, the variational variational method of interpreting the Schrödinger equation, and therefore the ground state. And so Feynman told us that you can't have the doubly degenerate ground state, because you can take a linear combination of wave functions which would vanish somewhere, and then you can lower the norm which gives you the estimate for the energy. So something should lift this perturbative degeneracy, and well, from the WKB methods, which are very old, we know that this degeneracy, which is the difference between the energies of the parity odd and parity even functions is non-analytic in H bar and exponentially suppressed. And this exponential factor is usually interpreted as the contribution of an instanton. So instanton, anti-instanton. Contribution. And so the way it is evaluated, you estimate the transition amplitudes of the Euclidean evolution operator between the between the states which are localized at the left and right minimum, or left and left, or right and right. And by computing the differences and sums of these matrix elements, you can, from that, you can estimate the energy split. And so it remains to evaluate this transition amplitude, and that's done by the sort of the saddle point method. So so if you look at this action, which I now redesigned after weak rotation and making data complex and taking it out of the integral, and also I changed the notation. So I sometimes use X and sometimes I use Q. So the equations for the critical point, and so that's the critical point in the complexified integration space. So the space of loops valued in the complexified phase space. It's a periodic solution of these slightly modified Hamilton equations. So this is what the equations look like. And it's quite beneficial to look at them in the phase space language, because if you do that the way it's usually done, only looking at the coordinate in the coordinate space, what you see is that you see the motion of the particle in inverted potential, essentially. And so, well, you would think that in order to find a solution which connects the left and right former minima, now maxima in inverted potential, well, you need to look for the trajectory which stays in the real space, and that's very hard. So what people say that, well, we don't know how to construct the solution when we move for the time beta, or in my units it should be exactly time 1, connecting minus v and v. So we'll construct a solution which takes at an infinite time and then do some hand waving. And so for the infinite time, you can find the solution of this equation, which actually will be the solution of the equation of the first order. And then you do some kind of interpolation, which is the way you construct instanton gas. So the reason it is misleading, and it's misleading for the wrong reason, is that if you look at the Hamilton equations, you see that even if you say that the coordinate is real, the momentum is imaginary. And if the momentum is real, then the coordinate is imaginary. So this trajectory does not want to stay in the real on the real slice. No matter how you try it, it sticks out to the complex phase space. And since it sticks out to the complex phase space, there is no reason to expect that this trajectory will have the coordinate which is real throughout the time evolution. And so that's how you lift this contradiction, which people usually live by forcing the trajectory to obey equations of motion for some Euclidean time, and then some interpolation, and then obeying another equation for the anti-instanton for the finite Euclidean time, and then jumping back and forth. So the instanton gas which people usually use, it is not a saddle point.
That's exponentially good, right? So.
But it's not a saddle point. So it means that if you expand the action around this configuration, you will have a linear term. So it will be first non-zero first variation. So you can then do another perturbation theory, you can shift your configuration, which I call x0 of t, which is a naive superposition of instanton and anti-instantons. You can shift it a little bit to remove the tadpole, and then you can iterate. And so in that way, this naive configuration of instantons and anti-instantons gets shifted. And I believe if you do it honestly, you will see that it gets shifted into truly a complex domain. So of course, this tadpole remove.
Sorry, for the zero mode, there is like a physical reason, because there's a gas, right, of instanton, so you need modular space and so on. So it's not a bad feature. So are you saying there are
this is all wrong. I'm just saying that this is all just trying to justify the means by reproducing the simple answer. But I'm saying that it should be done in a different way. So it's simply that the fact of the matter is that there are simply an infinite number of saddle points, and so each saddle point contributes something. The saddle points do have zero modes, but they're actually much fewer zero modes than instanton gas. And so I'm saying that in this case, because of the presence of the massive scale, which is the curvature of the potential, which allows you to say, well, all these errors are really exponentially small, so they would correct, they will show up at higher order terms, which will be irrelevant for this first exponential correction. In other cases, like in the two-dimensional sigma models, which I want to consider next, we don't have that scale. And so that's why I think it's much more important to understand the saddle point picture much more precisely. All right. So what are the true saddle points?
But you also can approximate it by real solutions with energy which is epsilon smaller than energy on the top, yes, in inverse potential.
Say it again. Approximate what? Sorry.
This summation. If you take particle which goes not right from the top to the top, but from minus epsilon, so it will approximate this instant.
But look, but this is also cheating. So I'm required to compute.
Yeah, I understand, but it's probably one of the way make regularization. No.
No, but the first it won't give the right answer. You still need to approximate. Even if you do this epsilon regularization, you'll find true solution. But still, you need to take into account all the instanton and anti-instanton, and they will be not true solutions.
Well, the point is that by shifting from V to V minus epsilon minus V minus epsilon V plus epsilon, you can find some solutions. But there are many more solutions than you see. The point is that the solutions are not visible on the real slice. Most of them are truly complex, and I will just show you. You will see where they are. It's not hard to see where they are. It's just that, well, mean, this shifting by epsilon is what of course, it's the first idea which comes to mind. But as my advisor told me, that you will not reproduce the entropy of the solutions. So you need something to reproduce the entropy of instantons and anti-instantons. That's what Colin just said. But that's trying to justify the I forgot what the end justifies the means. So you want to justify the means by fitting the answer. So this is not. It's good when you're at the frontier of science, but 50 years later, you would like to have some, more more systematic approach. All right. So what are these true critical points? Well, it's not hard to figure it out. You see, since we're solving the Hamilton equations, even though we have some modifications to what we call the Hamiltonian, basically it's the same. It's a Hamilton equation, except that we now allow P and X to be complex. But since it's a Hamilton equation, the value of the Hamiltonian is conserved. We don't know what the energy is. So it may well be complex. So what we know the initial in the problem of computing the trace, we know that we want the solution to be periodic in time. So that's for the trace. And if we want to compute the matrix elements, we know that the solution has to be at x equals to 0, it should be minus v, and then for 1 should be plus v. This is for the matrix element. So this is all we know. So for each saddle point, which would be a solution of Hamilton equations with this given boundary conditions, it would be characterized by some value of the energy E, but this value can be complex. And now, if it is so we know it has to be conserved. So it means that the trajectory belongs to the complex curve given by the equation h of px is equal to E, which for the harmonic oscillator is just an elliptic curve. So it's so topologically it's a torus, which means that my trajectory, and we will solve it in the general case in a second. So the trajectory is actually a kind of a straight line on this elliptic curve, which shoots at some angle and then winds around the cycles of the elliptic curve. Now, the elliptic curve has 2 cycles, and so this trajectory a priori is characterized by 2 integer numbers, p and q. So this trajectory will wind p times around the a cycle and q times around the b cycle. So if I write the class of gamma in h1 of the curve, so this is called curve with coefficients of z. So this gamma is characterized by 2 integers. So there is some topology which emerges, which was not in the present in the phase space. So it's kind of emergent. I like to call it an emergent topology. So now you see that. So this is the replacement for the missing entropy of instantons, anti-instantons. So one of these numbers is indeed it's a number of instanton anti-instanton pairs. But the second number you haven't seen before, and what this number is, it's roughly speaking the number of perturbative quanta which you can add on top of the instanton anti-instanton pair. So,
Nikita, sorry to interrupt. Is this curve smooth?
Yes, because for generic E, it's smooth. Yes.
Right, but if you go to the top of the potential, it degenerates, doesn't it?
Yeah, but then it's so for finite beta, the solution will have some value of E, which we need to find what it is. But it's very unlikely that you will be sitting exactly at the energy equals to 0 or exactly equal to the top of the potential, because at that level it will typically take an infinite time to really go to,
so you need to do what Zhenya suggested, right? Go to V minus epsilon.
No, absolutely not. No. The trajectory is fixed by, so this energy E will be found from the condition that at the moment of time 0, you're sitting exactly at minus V. At the moment of time 1, you sit exactly at plus V. E, so this guy E will fine tune itself so that the trajectory obeys your boundary conditions. And in a periodic case, E will fine tune itself that you have a trajectory which comes back in exactly the time beta.
Yeah, but this if you insist on that, then you're below the instant, because otherwise beta would be infinite.
Right, but beta is not infinite. Beta is very large, but it's not infinite.
I see.
So, so if I plot this on the plane of the energies, so the phase space, instead of the px space, it can be equally well represented by the fibration over the E plane, with the fibers being these curves CE. And so there are indeed two special points. So this is E equals to 0 and E equals to probably lambda V to the 4/4, where these fibers degenerate. Otherwise, oops, what happened? Otherwise, you are otherwise the fiber is a smooth curve, and then we so over each E we can shoot the trajectory, which will go around, but typically it will not come back. So it will keep winding and winding and winding. It will not close up to a finite number of windings. So you have only very special values of E, kind of a solar system of special values E, which depend on the choice of P and Q, for which the trajectory is, closes. So these are not, okay, so once again, so these are the parameters of the solutions. This is not the actual energy of the physical Hamiltonian. It's just that these are some auxiliary things which we'll have to sum over. And I call them a solar system because when beta is large, you can actually see some hierarchy. So they do tend to be exponentially close to the degenerate case equals to 0. So they do have exponentially small. I mean, they are exponentially small. When omega 0 is the scale, so it's a frequency of the perturbative oscillator. So, is there a question?
So this high energy is when they return back in time 1, right? As well. And then it also depends on beta, the configuration of these points. Right?
Yes. But they're also complex. So there is a second parameter Q, which is roughly speaking places them in this like orbits. So for given P, you have roughly P values of the variable Q. So qualitatively, what these two numbers are, if I go back to this picture with potential, even if I go back to the original potential, so P is roughly the number of tunnelings you do between the left and right wells, and Q is a number of rotations you can, which are classically allowed, which you do around this minimum. So when Zhenya was suggesting putting epsilon, so this epsilon effectively you have a complex epsilon which you don't see in the real slide, in the real projection, and you have several values for this epsilon. So in the modern language, since we are already 25 years past the Seiberg-Witten theory, so P and Q are like the monopole, and so like magnetic and electric charge. So P would be like a number of monopoles. So these are the tunneling effects, and Q is a number of W bosons, which you can put on top of each other. So these solutions, they look like dions, but these are dions in the four-dimensional supersymmetric gauge theory, which a priori has nothing to do with anharmonic oscillator. All right, so this is what these two saddle points look like. And,
so you have two parameters P and Q, but at the end of the
integers,
day,
integers. These are integers.
But
so
at the end of the day, they should kind of translate into integral of modular space within like n instantons, right? Sector.
There is no more. So the modular space is very simple. So let's describe the solution. First of all, let's describe the solution, and then we'll see what is the modular space. So the modular space are actually all identical. Namely, if you have a trajectory like that, then the modular space of this trajectory is just a circle. You can translate it along the torus. So you can start on this torus at any place you want. So this modular space is kind of a flat trivial space. So what used to be obtained by integrating over the positions of instantons and instantons, and that's where you got this exponentiation which produced the shift in the energy, now is obtained as a result of a summation over P and Q.
But so one of them will be the instanton number, kind of. If you go
yes, as I said, so P is like the number of instanton and instanton pairs.
And then some
but it's like qualitatively.
Yeah.
And summation over Q with a fixed P is, in my mind, it's like dressing the. So this is like trying to do the exact this. Take into account instanton and instanton interaction. So this is dressing the non-perturbative solution by perturbative fluctuations. But this is done exactly. So this is here. It's an exact thing. So it's a nonlinear superposition of instantons and perturbative quanta. So I would like to see the similar picture in first of all in the more general case, and then and in the high dimensional case. So first, let me just say one cute thing about the general case. By general case, I mean the case of a classically integrable system whose complexification is the algebraically integrable system. So that means that after complexification, my phase space has the structure of the fibration over the base, which is a complex space of half the dimension, and the fibers are abelian varieties. So they're complex tori, complex compact tori. So they have the form of the quotients of a vector space by the lattice. So the usual action angle variables of the classical mechanics in this algebraic integrable case become the interesting story of action angle variables, where you have many choices for the action variables. So in the usual Liouville story, the action variables are given by the let me call them I, the periods of the PDQ form over the cycles of the Liouville tori, and in the real case, the number of cycles is precisely the dimension of space. So this is in the real case. But when you complexify and you have this nice abelian variety structure, the number of cycles is twice as much as the dimension of the space. And so you have many choices for the for what you call the action variables, and that's exploited in Seiberg-Witten theory in the duality. So when you can choose the cycles like A cycles, you can choose the B cycles, you can choose half of some part, some fraction of the A cycles, some fraction of the B cycles, And there are some transformations between all these choices. Now, because of this double ambiguity in the angles, yes?
So, sorry, Nikita, maybe a quick precision, but in this case, with the complexified abelian varieties, you know this, suppose you do your complexification of the phase space and you go to action angle basis, but then according to Arnold, you must know the symplectomorphism to proceed with this, right? Otherwise,
You must what? Sorry?
symplectic max, symplectomorphism to action angle basis. How do you find them in this case? Because I think it is not always possible. But
no, of course not. Of course not. But that's okay. So that's the. I mean, that's a classical problem. So it's I'm assuming that we already know that
okay.
We know that the space has this structure. Then it's
sure.
This map to the action angle variables. If you know the structure, then it's explicit, because then the A's are just as I just wrote. It's just they're just the periods of the canonical form over the cycles of the Sibelian variety, and just the new feature compared to this Liouville Arnaud story is that these cycles, the choice of the cycles is not unique. You have more cycles to choose from.
Right. Okay.
So and that's important for this feature, for the structure of the solutions, because the corresponding angles are now, so you cannot normalize them that some of the periods are just integer multiples of 2 pi, but then the other periods will be a priori some non-trivial complex numbers which depend on the values of the action variables, and they're parameterized by a period matrix, which is a symmetric matrix with the positive definite imaginary part. And what's important is that there is some so there is this integrability story, a special geometry story, where this period matrix is actually the matrix of second derivatives of some locally defined function. So if I solve the Hamilton, these complexified Hamilton equations in these complex action angle variables, my solution would be a linear trajectory in these angle variables, and the condition that it closes after after time 1 means that the difference of the angles at 0 and at 1 should be one of these periods. And so I have 2 vectors of integers which parameterize the possible solutions. Well, this equation, so this is just rewriting that equation, the velocity, the angular velocity is given by the derivatives of the Hamiltonian with respect to the action variables. We want this to be some combination of integers and the matrix of periods. But because this matrix of periods is a matrix of second derivatives, you can partially integrate this equation and rewrite it as a condition of the critical point of some analytic object, which has a meaning of a superpotential, which is defined on the universal cover, on the partial cover of the base of the integrable system. So you don't. Okay, so there is some gain of the number of degrees of freedom. So this is the formula for this function. It involves some periods of the symplectic form, and a priori it's a transcendental equation, but it is what it is. So in the limit beta goes to infinity, we can approximately solve this equation by expanding near the discriminant. So the structure which I wrote here is that in the base of this integrable system, there is a discriminant of the singular fibers, and you expect the solutions for large beta to accumulate near the discriminant. Sorry, my drawing is getting worse and worse. So I'm drawing a picture of a discriminant from the singularity theory. It's a typical structure. It's like a swallowtail singularity. So that's what you may expect for most algebraic integrable systems which admit mutualization. And so the systems which we know following this classification are many body systems like elliptic Kaller-Moser system or Neumann system, which was actually the first algebraic integrable system discovered before the notion was invented. That's 150 years ago. And then the geodesic flow on the ellipsoid in general dimension, which is actually also the same thing as a Neumann system. So all the systems that meet the description of that type. And so, right, so now, and the general case, I mean, it seems that a large but not exhaustive set of such systems is known under the name of Hitchens systems. And we know that they have intimate connections to gauge theories. And so this structure, which I found here, is actually turns out to also have a meaning in some gauge theory. So it's some kind of a superpotential. And so we have ways of computing it, which is completely transcendental from the point of view of the original mechanical system you start with. So it uses the instanton counting of four-dimensional gauge theory. It's a different instanton counting, but I don't have time to explain that part of the story. I want to, so do I have like 5 minutes? It seems like I was slower than I expected. Even though I prepared some slides.
It's not 1 hour long. Normally, it's infinite.
Oh, okay. So, well, I do have some upper bound though. Okay, let me talk for 20 more minutes. And then I start.
Yeah, but maybe we
have a break in the middle. Do you want to make a break before you go into?
I don't want to have. I don't want to make a break. People can ask me questions, or you want to talk to yourself among yourselves.
No, we have like a tea break, relax a bit. I don't know if you.
But I'm in different time zones, so my all right.
But also,
okay.
I have a question.
Okay, how about 5 minutes? Yes.
Yeah, 5 minutes. Yeah, let's do 5 minutes.
All right.
So
Let me get some coffee.
Recording.
Okay, so I want to, yes. So now I want to pass to the real stuff, which is well, at least, I mean, ultimately I want to go to the Young-Mills case, and just as a maybe as a tease. So let me just tell you something amusing. So if you take the SU2 Young-Mills theory, and classically, of course, there again, if we follow this philosophy, and let me say that I want to take my space. Well, classically, it's conformal invariant, so I can look for solutions on anything which is conformally flat, for example, R cross S3. And I can take it as an ansatz. So A is an SU2, but now we complexify, so it will be the SL2C gauge field. So I can look for the solution for the gauge field of the form, which is like a pure gauge, where G is the map from S3 to SU2, like a tautological map, times some complex valued function of T. So T is time. So this is just an ansatz. Of course, there is no justification that this is in any way complete, but it just shows that the configurations, this phase space of Young-Mills theory already contains, upon complexification, this interesting homogeneous curves, and it is the elliptic curve for the SU2. So if you substitute that into the Young-Mills functional, you will get now the integral over time of so you get a harmonic potential. And so the usual, the instanton, now the gauge theory instanton is the usual tunneling between f equals to 0 and f equals to 1. But again, in the spirit of the previous discussion, if I make time periodic, if I want to study the Young-Mills theory of finite temperature, I would see those windings now of the elliptic curve in the Young-Mills case as well. So it's all relevant for the high-dimensional story. But of course, this is just an ansatz. So let me try to say something without going to the ansatz. So let's consider the sigma model valued in a sphere, or one can also take the projective space. And immediately, so we follow the same philosophy, we would complexify the phase space and in particular the configuration space. So, so the configuration space complexified will be the maps of the Riemann surface, which I will take to be a two-torus, to the complexification of my target space. And so now this is just the it's a hypersurface in the complex vector space. So C to the n. And so its real slice is the sphere, but other real slices contain ADS spaces. So the saddle points which I'm going to describe, they cover all symmetric, all ON symmetric spaces for different choices of signatures. Now I want to study the case of the Riemann surface being the two-torus, so that my partition function will have the Hilbert space interpretation, and I want to employ the symmetry, the ON symmetry, to discuss the twisted partition function. Actually, in my quantum mechanical case, I was doing that without being very explicit about it, because when I consider different matrix elements connecting left and right or left and left, that's like inserting the parity operator inside the trace. And so in the quantum mechanical case, my symmetry was just Z2 symmetry of the potential. In the spherical case, my symmetry is the group ON, and so I can insert the group element under the trace. In addition, I can also modify the Hilbert space by allowing twisted loops, so that my maps are, if you think about them two-dimensionally, they're twisted both in space and time. So this is roughly the boundary condition which I want to impose. So here sigma is space, and it's just 2 pi periodic, and time again has some periodicity beta, and I want my map to be periodic up to a twist by the flat ON connection. So which means that this twist should commute. So GH equals HG. Now, as conventional in two-dimensional case, we can also insert the momentum operator. In addition to the time evolution, we also have space rotations. And so that gives me another parameter in my trace, which is equivalent, of course, to studying the sigma model on the torus with a metric which depends on beta and theta. So usually we combine them into a complex quantity tau, which is essentially theta over 2 pi plus I beta. And so tau is a complex number with positive imaginary part. But again, I can now complexify, so I can study this quantity for complex separate complex beta and complex theta, of course, with some restrictions for convergence. So a priori, tau and tau bar are independent. Okay, so we'll come to that later.
So can I ask some basic question? So
yes.
Now we speak about quantum field theory, yeah. So and these maps in quantum field theory, they should be regularized with some cutoff somehow. There should be prescription, about renormalization. Yes, and if now you want to complexify, somehow you need to complexify these things. How you regularize your fields, etc.
Well, here I'm being very naive. So I'm saying that my path integral. Well, it has some cutoff, so maybe there is some finite dimensional approximation to the space of fields. Maybe so naively you may want to replace your Walsh. Maybe you want to replace your Walsh by a lattice, but actually I will produce a much better finite dimensional approximation. So lattice is actually not a very good approximation. But the point is that I mean, okay, of course, no, maybe jumping ahead of time, we know from the classical results that this theory is asymptotically free, which means that microscopically it should be well approximated by the classical Lagrangian. And so the classification of the contours of integration for my path integral of this quantum field theory should follow the classification of the saddle points of the complexified action. What you do with the saddle points is the next question. This is where the regularization and renormalization will take place. But the classification of the saddle points is just the classical problem.
Yeah, but phenomena like dimension transmutation, how it is how it will.
Oh, that's already determinant. And so
it's what you do with the saddle point, right? It's so again, so the infinities which you need to regularize and you deal with are the consequence of fluctuations around the saddle point. Okay, so the first business of the day is to classify the saddle points. So that's what I want to talk about. So what are the saddle points? Well, we formulate the Sigo model as the linear Sigo model with constraint, and that's what I want to do. So the equations of motion, as is well known, of the OM model, they're equivalent to the Schrödinger equation with a potential which is expressed through the solution. Okay, so through the solutions of the Schrödinger equation. So first I need to solve the Schrödinger equation for some potential u, and somehow it must have precisely n zero modes, which should be twisted periodic with the periodicity conditions which I imposed here. Or if I split let me take for the brevity the case of even n, so then I can block diagonalize my twists, and the eigen spaces will correspond to the splitting of my coordinates into pairs, so that the twists will have the form of the abelian twists with some identifications that you have twist H and H inverse and G and G inverse along space and time directions. And now, so we want all these guys, Z and Z tilde, solve the same Schrödinger equation. And so this Schrödinger equation has operators D and D bar, which are some complex combinations of D by dx and probably something like that. Where, once again, I don't assume tau bar to be complex conjugate to tau. So this operator is already, it's not Hermitian in the usual sense, but I don't care. It's formally self-adjoint, it's elliptic, and it doesn't deviate too much from the conventional Schrödinger operator. So the question is how to analyze this problem, how to find the solutions, how to characterize the potentials for which the potential itself can be reconstructed from the solutions. So, and once again, U is okay. So so this is once again this same problem reformulated in more explicit terms. So it turns out that a convenient way to approach this problem is to start with a generic Schrödinger potential, associate to it a certain analytic object, which we call the Fermi curve. So this is going to be, so it's complex analytic curve. A priori, this curve has an infinite genus, and then this alternative to the lattice regularization of the sigma model is the proposal to consider those potentials which this curve has a finite genus. But then, so that was our original approach with Krichever. But then we recently have actually proven the theory that actually all solutions of the sigma model equation for being the generic twists, at least the generic twists, they fall into this category. So this curve actually happens to be a finite genus, even though the genus could be very high. So in that sense, the sigma model looks like an infinite collection of these algebraic integrable systems of increasing dimensionality, which I think is exciting result. But what is okay? So what is this Fermi curve? I'm about to run, so just basically you look for the solutions of the Schrödinger equation which are simultaneous, which are also the Bloch solutions. So Bloch Floquet-Bloch. So they so the potential is doubly periodic. So U is and the solution just gets multiplied by some multipliers going around A cycle and B cycle on the torus. The fact that solution that psi solves the Schrödinger equation imposes some constraint. So this A and B are not independent, and it actually in the space of possible twists, which is the two-dimensional algebraic torus, the pairs A and B for which there is a solution of Schrödinger equation, those multipliers form a curve. So there's one relation. So the Fermi curve is actually not the space of multipliers, but it's certain resolution of singularities of that object. So it's normalization. So just to give you a flavor of what this curve is, let's consider the case of the constant potential. Then of course we know how to solve the Schrödinger equation very easily. These are just plane waves, and then fixing the constant imposes the relation between the two components of the momentum or quasi-momentum. So then these multipliers A and B are expressed in terms of a single variable k. K is a complex variable. And so as k changes, my multipliers A and B, they form some curve in this space of Bloch multipliers. But what you discover after a simple calculation is that there are infinitely many pairs of points in the k space which map to the same point in the space of multipliers. So it's the solution of some quadratic equations. So for each pair of integers m and n, non-zero integers, you have a double point in this the space of A's and B's. So this curve looks like a kind of a lattice, but it's a complex lattice. So it's sorry, grid, like a grid. So what happens when you perturb the constant potential with the Fourier modes, with non-trivial Fourier components, is that the Fourier mode with numbers mn resolves double point corresponding to the number mn of the Fermi curve for the constant potential. So these double points, they become little tubes, little handles. And so we will call the Schrödinger potential a finite gap potential if the corresponding Fermi curve is actually of finite genus. So after you perturb the potential, the dispersion relations become less singular, and so the curve becomes a finite genus curve. A priori, it's not the case. So if you just look at the Schrödinger potential, the generic Schrödinger potential will have an infinite genus Fermi curve. But the claim is that the Schrödinger potentials which you produce from the sigma model will have the curve of finite genus. It's a bit I mean, the theorem is, I think it's beautiful, but it will not have time to prove it here. Let me just conclude by saying that once you can reverse the procedure. So you have this curve, and this curve has two special points. So these are the analogs of the points when k goes to infinity and k goes to 0 in the for the constant potential case. So near these points, the function psi, which solves the Schrödinger equation, behaves as purely holomorphic or purely anti-holomorphic. So you have two local coordinates on this curve near the points p plus and p minus. So these are the points where the solutions become chiral. And then there's also the involution, which maps k to minus k. So all this we've seen in an example of the constant potential. These features are present for all Schrödinger potentials. So if you have a solution, there is a formally conjugate solution of the Schrödinger equation because it's self-adjoint in the formal sense. So that's just flipping the sign of the spectrum of this quasi momentum k. And so instead of starting with potential and then looking for all this data, you could start with this.
Oh, Nikita, your sound disappeared. Is it only me?
No, the sound is gone.
Nikita. I know.
Can be reconstructed as in terms of theta functions on this curve, on the one hand, and on the other hand, the potential will be reconstructed also in terms of this theta functions as some. Well, it's just dd bar of psi divided by psi. So all that you can find in our paper. And the additional structure that there is also a meromorphic function on this curve allows you to reconstruct the components of the vector, which describes the sigma model solution, as the residues of the Baker-Heisler function at the poles of this function.
But Nikita, sorry, so just to bring it to familiar context, so the algebraic curve for ON sigma model and so on, so that was studied before, obviously, and Baker-Heisler.
No, this is a completely different curve. So that's the point. So the curves which people studied before using basically the reductions from principal chiral model and Pomeroy reduction, they are not very well suited for the boundary conditions which I'm imposing. And so it is actually not, still not known what's the relation of our curves to those curves. So they must be related, but it's not clear what's the precise connection. So probably one covers another, but it's not a well understood question. So just to give you an example, it's not the first time in this business of PDEs where there are two curves for the same problem. If you look for the solutions of Bogomolny equations, so that equation, if you solve it on R3, so there is a twister curve, and that's it's unique, and that's the so the curves which Kolya mentioned are the analogs of this twister curve. So this is what it's related. From that you can get the principal chiral field into D and sigma models. So the curves which you get from the zero curvature condition, probably that's what you meant, right? So the spectral parameter for the zero curvature condition actually has a meaning of a twister parameter, which is a choice of the direction on this R3 or a choice of complex structure. If we impose a periodicity condition, at least in one dimension, so instead of R3, we'll talk about R2 cross S1, then there is another curve which you can define, and that's the spectral curve, second curve, which is more algebraic. So this one actually is kind of, so it's analytic, but it's kind of transcendental, actually, because the so this twister curve is built using the connection, which depends on the spectral parameter, and the connection is algebraic, but the monodromy data of this connection is transcendental. So the monodromy data will involve pathological exponential. So here, when you have a compact direction, the second curve is obtained by looking at the spectrum of the so you have a circle in the physical space where you take a connection along the circle shifted by the Higgs field. And as a function of Z on R2, so this is the curve. So that curve is kind of more algebraic, and the equations, so the Bogomolny equations can be solved in terms of the linear flows on that curve as well. And so that second curve is more like the curve which we're considering. So this is more like the analog of the Fermi curve, closer. Okay, so even with these Fermi curves, in order to impose all the constraints, including the constraints that the solution which we have lives over a two-dimensional torus, that imposes the set of these curves is actually isolated. So these curves don't form a modular space, unlike the if you think about the sigma model in general, if you don't impose the periodicity conditions, of course, you have a curve for every initial condition. And so then you have a whole family of those curves. But here again, we're trying to mimic this problem of finding the periodic orbits in quantum mechanics, in which case the solutions were forming discrete sets. And so in the single model case, we also have only the discrete sets, big but discrete sets of those curves. And remarkably, even though at many steps it looks like these periodicity conditions translate to transcendental equations, we have good indications that these curves can be characterized algebraically as special curves of elliptic Kalayjara-Moller system, which is much more algebraic than the initial problem suggested. The number of particles of this Kalayjara-Moller system can be very large. So it is not related to the dimension of
all algebraic. You mean it's better analytic?
Algebraic I mean algebraic. So like you can write it in polynomials, not in the transcendental function.
No essential singularities.
No essential singularities, right? Okay, I'm sorry, I have to run. So I hope I give you the taste of this subject. I think it's a hopeful new development. It's obviously just the very beginning. We know next to nothing about the fluctuations around the solutions. And maybe one thing which we can sort of see is that most of the solutions have this potential U, which has a non-trivial, non-zero average. So the dimensional transmutation, which we know happens at least for large n, the dimensional transmutation can be characterized classically as the fact that this potential U has non-zero zero mode, which acts as a mass, essentially as a mass squared of the classically massless fields. And so so that's just, it means that in computing the path integral, where we will be averaging over the ensemble of the subtle points, the fact that so this average means that it's the integral of the two-torus. The fact that the typical solutions come with non-zero value of the mass sort of confirms that the mass will be generated dynamically in this point. Okay. Thank you.
Yeah, thank you very much. Let's unmute ourselves, and thanks, Nikita.
All right. So I'll see you later. Bye-bye.
Right.
All right. Thank you. So who we ask the question then?
I guess we can stop recording.